Okay. I think it's working now. Extended capture, stop capture. Okay, oh, extend capture. Okay, I think we're currently working, and you should be able to see something on the screen, which would be just a pen here, maybe. No, I'm not seeing anything on the screen. Okay, so touch for screen 1 source. So I'll put document camera 2, and is anything coming up? Hold on. Touch to send to screen. Okay, it should be. Okay. Why is it not coming up on the monitor, though? Okay, so the question is whether I have faith here. Oh, there we go. Okay, good. So we're getting up. Okay, so I think that we now have a functional system. Okay, so we're going to next. Okay, so we have. Oh, maybe what I could do is go to the computer and. Hold on. Well, no, I don't think we have any. Okay. Unfortunately, what I should have thought to bring with me, and it didn't occur to me, is actually examples of the lab output. Maybe I should go to, you're doing the lab, right? So let me go to touch for screen 1 sources. So we'll go to the PC, okay? And maybe the PC will come up. Will the PC come up? Is the PC coming up? No, the PC is not coming up, right? Does anybody... PC, right? PC. Does anybody see a PC here? So why is that not coming up? Monitor. No, it's still the display. Touch to send to screen. Is it working now? Oh, okay. So now you see the computer screen, right? And what I'm going to do is go to the laboratories, and you're working on this laboratory right here, right? So unfortunately, I don't have, this is the actual image, I guess. It's not opening it, though. Huh, oh my gosh. Wow, I have to open up all Photoshop. I'll just open up this TIFF, huh? Well, oh my goodness. You would think opening a TIFF image would be a relatively straightforward matter, wouldn't you? Okay, maybe we'll not worry about that. What the heck is it doing? Okay. This is the laboratory procedure. Open. Okay, so here's the laboratory procedure, and oh, there's the image. Okay, so you're going to add noise to this image and restore it, and then you're going to blur the image and add noise to it and restore it. So, and you're going to do this with the quadratic prior, but when you have more regularization, the image will look blurrier. When you use less regularization, the image will look sharper, but there'll be more noise, okay? But effectively, what you're going to find is that in the end, whenever you have quadratic regularization, the solution is always linear, right? Because if we go back to the theory of all this, the solution to the problem has the following. Notice I'm sort of stalling here because I always look for the answer. Oh, here it is. The solution to the problem is that x is equal to, for the quadratic case, is equal to A transpose A plus sigma squared B inverse times A transpose Y. Oh. Okay. I need to go to the document camera again. Okay, right. So you see that. right? And so this is a linear operator. So when you solve, but the way we're going to actually find this solution is we're going to minimize over x the norm of y minus ax squared plus x transpose bx, right? So we're actually working on this problem, but our intent is to solve that problem. These are two different formulations of the same problem, okay? So when we do this, we're going to get a linear, our solution is a linear operator applied to the data. Well, linear operators tend to smooth data, okay? So essentially what's going to happen is that the linear, oh, and by the way, if our model for A is that it's space invariant convolution, and our model for B is that it's a homogeneous Markov random field, this is going to be just this will be a linear space invariant filter. So this is going to be just a filter. So linear filters smooth edges. So basically what's going to happen is that you're going to have a trade-off. You'll either get blurry edges or you'll get a noisy image. I mean, it's not really going to come out that good. So this is okay in a lot of applications, because in a lot of applications, what's really happening is that the image is blurred by some kind of linear filter, and that's really what's happening, and so that's an accurate model. This part here is not okay. Okay, because the image is really not. Why is this not okay? Because this is implicitly assuming that the probability distribution for the image has the form exponential of -1/2 x transpose bx. Okay. So what you're assuming is Gaussian. But images aren't Gaussian. Actually, as a matter of fact, if you take pixels in the image, I should do this, or you guys should do this. Why don't you guys do it and then produce a plot for me and bring it to class, and I'll show it to everybody else. Do a histogram of the difference between neighboring pixels in an image, and the histogram will look kind of like this. It's typically reasonably modeled as Laplacian. So the probability of delta here is like e to the minus delta over sigma here, and then there's some kind of normalizing constant for the integral to come out correct. It might be like 1 over 2 sigma. Is that correct? That may even be correct, but it's something, okay? So it's not Gaussian because when edges occur, they're sparse and they generally have very large amplitude. So this model is not very good, and that's one reason you get not such good images. Okay, so then what you do is you say, okay, well, what can I do that's better? So that's chapter 6 now, which is we're going to go to non-Gaussian models. So when we go to a non-Gaussian model, and in particular we'll do non-Gaussian Markov random fields, okay? And these are going to be continuous. By continuous, I mean that the pixel values vary continuously. So sometimes we represent them as going from 0 to 255, but for this class, you better use double precision floats, okay? So they're continuous variables on the real line. Okay? And then, so how is this going to work? Well, okay, so we want to model this thing as being non-Gaussian. Okay, so there's some kind of interesting things you can do. Well, first of all, it's kind of an interesting identity, and you'll show it, I think, as a homework, that x transpose bx is equal to, well, I'm not even going to write it out. It's equal to this. Let me just zoom in. How do you zoom in? Oh, zoom in. I'm going to assume that's zoom in. Okay. So it's kind of an interesting relationship. So you can write this quadratic form in terms of a sum over pairs of pixels squared. Now, and you also have to include a term associated with individual pixels squared. But you can show that this is true pretty easily. You just take some derivatives on both sides and equate some things, and this pops out, okay? But it's not a relationship that actually you see around very often. The interesting thing is A here, for each f, for each pixel f, A sub f is going to be the sum of a row of B. Now, B is a symmetric matrix, so you can either sum the row or the column of B, okay? So let me draw a picture. So if this is B, and that's the fth row, you sum along this row, and that sum is going to be A sub f. So you sum along a row, and equivalently you could sum along a column because it's a symmetric matrix. Now usually what will happen very often is that that row will be 0. Often A sub f equals 0. Why? Because what will happen is that, okay, in the center position you'll have, like, let's say this is B, okay? You'll have this matrix B. So F comma R, right? Now, we know that B of F comma R is 1 over sigma squared, where that's the non-causal prediction variance, okay? And then there's a delta, right, at when S and R equal, and then minus G of S comma R, okay? Like that, right? And so what's going to happen is that if I sum this, the sum over R of B of S comma R, that's going to just be 1 over sigma squared, okay, times, the delta here will be just 1 when I sum over it, right? And then this will be minus the sum over R of G of S R. But very often, this is the average of the neighbors. So this is the weighted average of the neighbors, right? Or the weighted sum of the neighbors. Very often that sum is 1. Right? So like if you picked the G's to be 1 quarter, 1 quarter, 1 quarter, 1 quarter, they sum to 1. And then you predict this center pixel at, oh, I gotta zoom out. You guys have to warn me when I'm doing something that makes no sense like this. Okay, so to predict that pixel, you take the average of the 4 neighboring pixels. So, so if that's the case, then this whole thing, which is supposed to be A sub f, is going to equal 0. So, very often, and in the problems we're going to look at, this is 0. Okay. So then you can just write this as a sum of pairs of pixels, the differences between pairs of pixels squared. And you have a weighting there, B of SR, and B of SR presumably gets smaller as the pixels get further away. Now, if the pixels aren't neighbors, what does B of SR equal to? 0. See? Okay, let me just say that one more time, okay? So we actually talked about this before. So the B, the matrix B, remember the matrix B? The matrix B, okay, the matrix B, so we'll take matrix B, it's going to have some elements on its diagonal. They're the inverse prediction variance, right? And what will happen is the non-zero elements, if B of SR is greater than 0, or let me just write it like this. If B of SR is not equal to 0, what does that mean? It means that XS and it means that S is a neighbor of R, or equivalent means R is a neighbor of S. So if the two pixels are neighbors, then the coefficient is got to be non-zero. Alternatively, if it's 0, well, they don't have to be neighbors. Okay, if they're not neighbors, it has to be 0. Okay? If they are neighbors, it can be 0, but it's sort of a trivial case in which they're neighbors that aren't very neighborly. Okay? So, oh, that was a little startling. And then, so only the neighbors. Well, all the non-neighbors are 0. Okay, what I'm about to say is false, but you know what I mean. The neighbors are all non-zero. That's not really true, but it may as well be. All the neighbors are non-zero. Okay. So the only time that BSR is non-zero is when these are neighbors. So you're just taking a sum over pairs of neighbors, and you're squaring the difference. So your assumption is that things that are neighbors should be approximately equal. The only time they won't be is if the neighbors fall across a boundary. So okay, so you can rewrite the probability distribution for X as a sum over pairs of pixels, a weighted sum of pairs of pixels. So for this, so for a Gauss Markov random field, I can write P of X as a sum over pairs of pixels. Now these are pairs of neighbors. Okay. Now this is B F comma R of XS minus XR squared. Now one thing you have to be careful about is that here, let me hold on for a second. Is that correct? No, that's got to be correct because I've been over this 1,000 times. Oh my God, this is an error. Just a minute. This is an error. I can't believe it. I found an error. I'm pretty sure that's an error. Sometimes when I leave the lecture and under the pressure I think something is an error and it's not. But that shouldn't be divided by 2, I don't believe. Because this is not divided by... Oh, no, it should be divided by 2. No, this is correct. Because you have 1 over 2, right? Okay. I shouldn't second guess myself. Okay. But there is something, the reason I'm confused about this issue of 1/2 is because it's a little tricky. Because over here there's a 1/2 because I'm summing over all pixels S and all pixels R. So that means if I have a pair of pixels, right? This is 1/2 and then this is exponential and then 1 over Z. So if I have a pair of pixels, this is S and this is r. I can sum over that two ways, because I can take xs minus xr squared, right? And I can take xr minus xs squared. So I have to be careful I don't count it twice. So when I use this notation here, when I use this notation, I'm summing over all s and over all r. So every pair of pixels gets counted twice. So I divide by 2 to account for that. But if I use this notation, I'm summing over each pixel, every unique pair of pixels once. So then I don't divide by 2. But over here, I worried, but I was in fact correct. When I actually write the distribution down, I divide by 2 because you divide by 2 in the Gaussian distribution. So, because remember, it's exponential of minus 1/2 x transpose dx. Okay? So this is the distribution. But so far, this is all the same. Now, what happens, though, is that we know if I take, say, delta SR is equal to XR minus XF, this is the change in a pixel value, right? And we know that if we plot, well, we don't really know this, but I'm sort of trying to intimidate you into believing that if we plot the histogram of that, we'll get something that kind of looks like this with heavy tails. Okay? So it won't look Gaussian. It'll look Laplacian. So we really want to model this distribution. So the problem is right now we're using xs minus xr squared. So as that difference becomes large, the probability of that event becomes much smaller rapidly. So instead what we're going to do is replace that function with something else. So we'll put in some function here, rho of xs minus xr. And later, and then what we're going to do is we're going to talk about how that function might be chosen. Okay? And then this thing here is called the energy. Okay? The reason is that if we have a probability distribution, 1 over z exponential of minus u of x. This is called a Gibbs distribution. And z is called the partition function. And u of x is called the energy. And if u of x is equal to a sum over, say, pairs of pixels of some function of xs, say, minus xr, this is called the potential function. And the reason that we give it these names is because this is analogous to quantities in thermodynamics. Has anybody ever taken a thermodynamics course? Oh, wow, that's pretty good. So the Gibbs distribution turns out to be the distribution you get when you're in thermodynamic equilibrium. And it can be, in fact, later on somewhere I have an appendix in all this. I think it's later on in in my notes, where it shows that the distribution, we call it the Gibbs distribution, but actually in physics they also call it the Boltzmann distribution. And it results by saying if the expectation, if I define the energy to be equal to the expectation of this u of x, right? Oh, I have to zoom out. And I define the entropy to be equal to the expected value of the log minus log of p of x, then the entropy of the Boltzmann distribution results from maximizing the entropy subject to a constraint on the energy. So the argument goes like this. In a physical system in equilibrium, okay, so it's kind of interesting. So why is it, for those of you who have never taken a thermodynamics course, why is it that if you have a ship, well, going down the ocean, okay, and we'll put a little smokestack here. Okay, you have a ship going down the ocean. Why is it that the ship can't just have a little propeller here? Okay, so that could be the propeller, right? And what it could do is, in order to produce the energy it needs, it could pop out little ice cubes. Well, how do you make an ice cube? Okay, so you could pop out ice cubes, okay, and then it would take the energy out of the water that it turns into ice cubes, and then it would propel itself through the water. Either this is a really great idea and you should all bolt out of the class immediately and patent it, or there's something wrong. So why doesn't this work? It doesn't violate conservation of energy. Does anybody know why this doesn't work? What law it violates? By the way, you know, when any people talk about having an energy crisis, it's ridiculous. We have plenty of energy. As a matter of fact, we have exactly as much energy as we started with, because you can't destroy energy. There's a thing called conservation of energy. So the amount of energy we have now is the same as the amount of energy we had at any time in the past, plus or minus like quantum mechanics and a few other things like that. But so what's the problem? Yeah, well, the entropy is going up in this system, okay? The entropy in a system, entropy is going down. So it's violating the second law of thermodynamics, which is that the entropy can only go up, okay? So a system in thermodynamic equilibrium reaches a stable configuration when the entropy is maximized. And the Boltzmann distribution maximizes the entropy subject to a constraint on the energy. So you can argue from basic principles that it's the distribution you get when a system is in thermodynamic equilibrium. So we're going to use an analogy to that. So you can think of the Gaussian distribution as being like the Gibbs distribution or Boltzmann distribution, where the energy is of the form where you're summing the square of the difference between neighboring pixels. So what system produces an energy which is proportional to the square of distances between things? So if you take a spring, a conventional spring, sort of the simple model for a spring, the force is proportional to the, so let's assume that the spring has zero length, okay, or somehow we adjust things so that that's the case. So what we could do is put it in a contraption where we're only looking at the change in length, okay? Okay, so this would be delta, right? And the force is going to be k times delta, where that's the spring constant, right? And then the energy is going to be the integral of that, so it's going to be k over 2 times delta squared. So the energy is proportional to the square, and the force is proportional to the delta, and in each case there's a k, and okay, so that's basically the deal. So essentially, what happens is that essentially what you're doing is your assumption here is that like the energy is proportional to the square of the difference between the pixels. So that's the sort of solution. So what you want to do here is, so if you plot the energy, so the force looks like this. This is the force, and this is the energy. Okay. Okay. Now the problem is that as the pixels get further and further and further apart, you're penalizing. So this has the interpretation of like a restoring force as you're displacing the pixels. They want to go back to be equal. So the problem is that when you have an edge, like all of a sudden the two pixel values next to each other will be quite different. So the restoring force will be very great, too great. So what you want to do is you want to adjust this to limit the restoring force. At some point you're going to say, well, okay, but come on, like if they're that far apart, I'm not going to just keep pulling. At some point I'll say, okay, I give up, uncle, and I'm going to chop it off. So if I do that, then what will happen is that if I stop this from going up, at this point the integral will become a constant. This will become a straight line. I may have drawn that perfectly, but it's drawn better in the note. So this is sort of the art of these so-called potential functions. That what I can do is I can write the distribution as this potential function of the difference between pixels, and then I sum those times this coefficient of the weighting, okay? And that's the probability distribution. And then there becomes sort of an art form to picking this row so that you get the right distribution. So you get an effective distribution for your problem. And when you do that, by the way, so typically what will happen is that here are some criteria you apply when you pick these functions. So one is that you want rho of 0 to be 0. That's not much of a constraint. That's just sort of a normalizing factor. It doesn't really matter, but it just makes things simpler to express. Okay, you want it to be a symmetric function, typically, and you want it to be monotone increasing. It doesn't actually have to be, but that's to be a typical choice. Okay, and then you can get some intuition by looking at the conditional distribution of a pixel given its neighbors. So this is like the prediction error you would get. So and if you look at the conditional distribution of the pixel given its neighbors, you get an expression like this. Now the part on the denominator is just a constant, so you really don't have to worry about it. It's the numerator that's important here. And what you're saying is that the probability of x is going to be the exponential of a sum over the neighbors of each pixel x minus its neighboring value evaluated with the function rho. So what does that mean? Okay. Oh, well, first of all, I forgot to point out something very important, which is that this is a Markov random field, because the terms that don't depend upon xr all cancel out when r is not a neighbor. So this thing will produce something which is only dependent upon neighbors. So this will be a Markov random field. Okay, so did I define a Markov random field? So, okay, so X is an MRF. What's the definition? It's an MRF if the conditional distribution of xs given xr for r not equal to s is only a function of the neighbors. So if the conditional distribution of a pixel is only a function of neighbors, that's the definition of a Markov random field. And this particular form is a Markov random field. That if this is the distribution, oh, hold on. If this is the distribution, we're calling that a pairwise Gibbs distribution. If this is the distribution you choose, then that's a Markov random field, and every pixel will only be dependent upon its neighbor, okay? Now, okay, so how do you pick these functions? So you need to go through this calculation separately, okay? Because I can't do this for you, but okay, the key issue is this. So you're going to have this potential how to choose potential function. So rho of delta, and delta is typically xs minus xr. It's the difference between two pixels. How do you choose it? Well, you have two things. Okay, so this, and then you have the derivative. This thing is called the influence function. It's the derivative. And this tells you how much influence a neighboring pixel has on another pixel. So, you know, this is a lot like you know, when you're hanging around with the wrong crowd, and your parents complain and they say, you know, you got to get better friends, okay, because they're providing a bad influence on you, okay? So you have some pixel here, and then you have the neighboring pixels, and you don't want these pixels to provide a bad influence on this pixel. So if there's an edge that falls in between here, you want this derivative function is going to tell you how much that pixel influences that. And the derivative, you just take a derivative of the influence function. So here is examples. Okay, this is the potential function x squared. This is delta squared. And this is the derivative. The derivative then is just delta. So this has unbounded influence. As the neighboring pixel becomes larger and larger and larger and larger and larger, it can affect the outcome and the choice of the pixel in question arbitrarily much. There is unbounded influence. So that's not entirely a good thing because it doesn't allow a sharp edge to form. Now, another possibility, which is a kind of a limiting case that doesn't really get used very much, is this so-called weak spring potential function. So the function, you just clip it off. You say, okay, enough is enough. Once I reach some value t, for any difference that's larger than that, I'm just going to stop. The energy won't increase. So essentially, one way to think of that is that you have a spring and you stretch it, and when it reaches some level, all of a sudden some kind of crazy mechanism comes into play. Like there's an let's say there's an electromagnet here, or there's a rare earth magnet, right? And once you pull it far enough, the magnet can't hold and it snaps, okay? And then it sort of disconnects. But the only thing is that when you go back again, it just reconnects at exactly that point again, okay? So the energy gets stored and it doesn't get wasted. In that case, the influence is the derivative of this, so it increases linearly up until it reaches that threshold, and then the derivative is 0. So the influence beyond that point is 0. So up until that point, you have linear influence, and then beyond that point, you have no influence. Okay? That's the so-called, sometimes people call that the weak spring model. Okay? And yeah, so when you go to, so that's, pretty much the deal. I mean, when you go to calculate the conditional distribution of a pixel given its neighbors, this expression you get will be that you want to set this is like a forced balancing equation where the derivatives of all the influence functions have to equal 0. So any pixel which falls too far away, it'll just ignore. But one thing that's kind of problematic about this is that doing the optimization in this case is tricky because this cost function is not convex. And we'll find out later that when you have non-convex cost functions, doing minimization is tricky. You can get stuck in local minimum. So you can imagine that you'll have problems when if the pixel decides it's in or it's out. It could be, you know, the optimization will be tricky. Okay. Now, let me see. Okay, so this is the mathematical formula. So the Gaussian is just taking the x squared, okay, and then the weak spring, you take x squared, the minimum of x squared and t. So whichever one is smaller, so you're clipping it off to value t, where t is, t squared, where t is the threshold. By the way, this now requires that you pick t, which is a parameter, and that can be a problem. So that's one disadvantage to this approach. Okay? Well, there's been a whole slew of these different things over the years proposed, and there are various ones, and I have them all listed out, and you can make up some more at home if you choose. You can just sort of draw some pictures that you like, but they pretty much kind of fall into certain kind of general categories. So this is the weak spring thing, okay? It just clips it off. And you can say, well, that's a little too extreme. So instead of clipping it off, what I'll do is sort of ease it over to smoothly blend into it being clipped off, right? And then I could also say, well, I'll do something a little bit more, yeah, I mean, like, you know, you kind of get the idea, right? Now, and often looking at the influence function, so the influence function is the derivative of the potential function. You kind of get a clearer sense of what's going on. But all these approaches are non-convex potential functions, and non-convex optimization is problematic. So let me just review why non-convex optimization is problematic. Okay, so, you guys know what convex optimization is, first of all. Okay, do you know what a convex function is? I haven't described that yet. Have I talked about that yet in this class? So, did I define convexity in this class, or I don't think I did yet in this class. In 637, but not in this class, right? So if you have a function f of x, okay, if it's convex, what that means is that, so the function looks like this. If you take 2 points and you draw a line connecting them, it falls above or on the function. So if I have, that means if I have 2 values, so then for all a and b and lambda in the interval 0 to 1, it must be the case that f of lambda a plus 1 minus lambda b is equal to lambda f of a plus 1 minus lambda f of b. Oh, not equal. That would be linear. This has to be less than or equal to. Because this, for any value of lambda between 0 and 1, is a point along the line. So this is a, and this is b. And the values are f of a and f of b, right? So that's the definition. And if I put strict inequality here, then this is strictly convex. Okay. Now, convexity is very valuable when you're doing optimization, because if you have a function that looks like this, right? Is that a convex function? But you see, you get stuck here, right? If you're doing optimization. if you have a convex function, you can't really get stuck because, gee, if I drew a line from here to here, then that would be putting like a ramp in where I could then roll from this local minimum to that, right? So you can pretty much prove that if a function is convex on a convex set, then so let's say a function is convex on Rn. If you find a local minimum so that the gradient of f of x equals 0, then that's got to be a global minimum. Okay. Right. So convexity is very strong because it's a way of ensuring that you can ensure that there is a minimum, and that most algorithms for doing optimization require something like convexity in order to guarantee convergence to a global minimum. Okay. It's a pretty strong condition, but it's necessary for proving convergence to a global minimum in most cases. Okay. So convexity is useful for that reason. Convexity is also useful for another reason. I guess I'll talk about this next time because I should check to see how much time we have. Hold on. Okay, we have 3 minutes. The other thing about convexity is that, let's say that you have a function, and you'd say, remember, we have these functions, right? Okay, so this is x, right, and this is f of x, okay? And then what we want to do is we want to compute x hat equals the arg min over x of f of x, right? Now, so let's say that the solution then is right here. That's the minimum. That's the global minimum. So we'll call that x hat, okay? Now, and this whole thing here, f is really, of x, is really a function of y, because we have data, right? So this whole curve is a function of y. Now, it could be that that you have this cost function, and maybe this minimum here is very close to the value of this minimum. So the position, the argument that achieves the minimum is very different, but the value of the function at those two positions could be very close. So now, if we just change y ever so slightly, this thing might tilt a little bit, and when it tilts, then all of a sudden the minimum could fall over here. So here you have a perturbation in y, an arbitrarily small perturbation in y could create a large perturbation in x. So this is unstable. This is unstable in the sense of it being a discontinuous function of y. So f is a continuous function of y, but the minimization of f with respect to x produces a discontinuous function of y. So in practice, that could show up like, I have an example in the notes where I show two curves, and we're almost out of time, but two curves, and this one results from a small change in the data creates a discontinuous change in the result. So make sure you read all the notes for next time, because we're almost out of time, and we'll meet again on Wednesday, and next week I will be out quite a bit. I'm going to actually go to Germany. So we do need these makeup lectures, but by the end of next week we'll be only, I think, one lecture ahead. Bye, and it was really nice knowing you today. And well, we're done. Okay. All right, good.